Have you ever stopped to consider that the universe might be speaking to us, not in words or symbols, but through the very fabric of space and time, through ancient light, ghostly particles, and the fundamental laws that govern everything from the largest galaxies to the smallest atoms within us? Imagine the cosmos not as a silent, empty expanse, but as a grand, cosmic library filled with stories written in the first moments of existence, just waiting for us to learn how to read them. Every time we gaze up at the night sky, we're not just looking at points of light, we're witnessing an ongoing conversation that started nearly 14 billion years ago, a dialogue encoded in everything we see, touch, and are. Today, we're setting out on a journey to explore 24 profound ways the early universe is still communicating with us in the present day. From the faint afterglow of the Big Bang, the cosmic microwave background radiation that blankets the entire sky, to the subtle elemental fingerprints in our very bodies that were forged in the first few minutes of creation, these messages are all around us, waiting to be decoded. They shape not only our scientific understanding of reality, but ripple into technology, philosophy, and our deepest questions about where we come from and where we're headed. This isn't just about astronomy or physics. It's about recognizing that the universe is dynamic, alive with meaning, and that we are active participants in its story. By the end of this video, you'll see the interconnectedness of all things in a new light, how the past isn't really past at all, but vividly present in the signals we're only now learning to detect. You'll gain a fresh perspective on existence itself, one that bridges the gap between the primordial and the personal, inviting you to listen in on a conversation that has been unfolding since the dawn of time. So settle in, open your mind, and get ready to see the cosmos and your place within it like never before. Picture the universe just 380,000 years after the Big Bang. Before this moment, the cosmos was an opaque, searing fog of plasma, so dense that light particles couldn't travel any meaningful distance without immediately crashing into and being absorbed by free electrons and protons. But then, in a pivotal cosmic event known as recombination, the expanding universe finally cooled enough for electrons to be captured by protons, forming the first stable hydrogen atoms. Suddenly, the fog cleared. For the very first time, light could travel freely across the vastness of space. That first burst of light, that initial flash of liberation, has never stopped traveling. It has been stretching and cooling with the expansion of the universe for over 13 billion years, and today, it fills every cubic centimeter of the cosmos as a faint, cold microwave glow, the cosmic microwave background radiation. This isn't just some ancient relic, it is the most important baby picture ever taken. The entire sky is painted with this afterglow, and it serves as a direct snapshot of the universe in its infancy. When Nobel laureates George Smoot and John Mather led teams on satellites like COBE and later Planck to map this radiation with exquisite precision, they weren't just looking at a uniform blanket of light. They discovered tiny, minuscule fluctuations, ripples in temperature that vary by just mere millionths of a degree. These tiny imperfections are absolutely crucial. They are the gravitational seeds from which the entire cosmic large-scale structure would eventually grow. Those slightly denser, slightly warmer patches were the sites where gravity began to pull matter together, eventually forming the vast webs of galaxies, clusters, and superclusters we observe today. But the CMB tells us so much more than just where we came from. It is a fundamental tool for measuring the universe itself. By analyzing the precise characteristics of these fluctuations, cosmologists can determine the universe's age with incredible accuracy, 13.8 billion years. It reveals the rate of the universe's expansion, the density of ordinary matter, and perhaps most profoundly, it provides the strongest evidence for the existence of the mysterious substances that dominate our cosmos, dark matter and dark energy. The way the light from the CMB is subtly distorted or lensed as it travels through the cosmos maps out the distribution of invisible dark matter. And the overall geometry of the universe, inferred from the size of those ripples, points directly to the presence of dark energy accelerating the expansion. This ancient whisper even hints at what happened in the universe's very first fractions of a second. The overall uniformity of the CMB, paired with the specific pattern of the fluctuations, is a powerful piece of evidence for the theory of inflation, the idea that the universe underwent a period of exponentially rapid expansion in the first fleeting moments after the Big Bang. This would have stretched quantum fluctuations from the subatomic scale to the cosmic scale, planting the seeds for everything to come. So every time you see static on an old television set, know that a small percentage of that snow is actually this primordial light, the universe's first communication, still arriving at our doorstep and telling us the story of our own origins. Now rewind even further back in time, to a period when the entire observable universe was not just hot, but unimaginably dense and compact, a seething nuclear furnace where the very first atomic nuclei were forged in a breathtakingly brief and violent burst of creation. Within the first 3 minutes after the Big Bang, the conditions were just right for a pivotal cosmic event known as Big Bang nucleosynthesis. During this fleeting window, the universe had cooled enough from its initial infinite heat for protons and neutrons to begin fusing together, yet it was still too hot for these new atomic nuclei to capture electrons and form complete, stable atoms. It was a frantic, high-stakes dance of particles, constantly colliding and combining in a chaotic plasma, all while the expanding cosmos rapidly cooled around them. This primordial alchemy produced a very specific and surprisingly simple set of elements, primarily hydrogen-1, the single proton that is the universe's most basic building block. A significant amount of helium-4, each nucleus a tight bundle of 2 protons and 2 neutrons, and only the tiniest trace amounts of a few other light elements like deuterium, a heavier form of hydrogen, helium-3, and lithium-7. What makes this process so astonishing for scientists today is the incredible precision of its predictions. In the 1940s, physicists Ralph Alpher, George Gamow, and others worked out the theoretical framework for this process on paper, calculating what the abundances of these elements should be based on the known physics of nuclear fusion and the estimated conditions of the early universe. Decades later, with the advent of powerful telescopes and spectroscopy, we began to measure the actual abundances of these elements in the most ancient places we can find pristine gas clouds on the edges of the observable universe, and in the atmospheres of incredibly old, metal-poor stars that formed before later generations of stars had a chance to pollute the cosmos with heavier elements. The agreement between those theoretical predictions and our modern observational data is nothing short of spectacular. It is a triumphant validation of the Big Bang model. The amount of deuterium we see, the ratio of helium to hydrogen, even the puzzlingly low amount of lithium that still presents a fascinating minor mystery, they all align almost perfectly with what we calculate should have been produced in that first 3-minute frenzy. This isn't just a historical curiosity, it's a powerful tool for modern cosmology, because the outcome of this nucleosynthesis was so sensitive to the conditions of the early universe, like its density and expansion rate, we can essentially run the process in reverse. By measuring the precise amounts of these light elements out there in space, we can tightly constrain fundamental parameters of our cosmos, such as the total density of ordinary baryonic matter. It even provides a unique probe into the particle world, offering insights into the number of different types of lightweight neutrinos that flit through the universe. This means the legacy of those first 3 minutes is not locked away in some distant corner of space. It is quite literally all around us and within us. The hydrogen atoms in the water you drink, the helium in a child's balloon, the very atoms that make up your body, most of them were created not in the heart of a star, but in the first few moments of the universe itself. They are the oldest tangible things you will ever encounter, silent messengers from a time before time as we know it really began, carrying a story of a hot, dense, and orderly beginning that set the stage for everything that was to follow. Now let's shift our perspective from the light that filled the cosmos to the very fabric of spacetime itself. Picture a calm, still pond on a windless day. The surface is perfectly smooth, a flawless sheet of glass. Then, a single stone drops into its center. In an instant, that perfect calm is broken by a series of expanding ripples that travel outward, disturbing the water's surface in a predictable, measurable pattern. This simple analogy helps us grasp one of the most profound predictions of Einstein's general theory of relativity: gravitational waves. According to Einstein, the universe isn't just empty space. It's a dynamic, four-dimensional fabric called spacetime, and the most violent, energetic events in the cosmos, like the collision of two black holes, can send ripples through this fabric, much like that stone disturbs the pond. These ripples are gravitational waves, literal distortions in the geometry of space and time that propagate outward at the speed of light, compressing and stretching everything in their path by almost unimaginably tiny amounts. While we have already begun to detect gravitational waves from recent cosmic events with observatories like LIGO and Virgo, which earned a Nobel Prize for their groundbreaking work, there is an even more ancient and faint signal we are desperately searching for: primordial gravitational waves. These wouldn't be from black holes or neutron stars, but from the birth of the universe itself. The theory of cosmic inflation suggests that in the first fraction of a second after the Big Bang, the universe expanded at an exponential rate, faster than the speed of light. During this incredibly energetic process, the microscopic quantum fluctuations that are a fundamental part of reality would have been stretched to astronomical sizes. It's believed that this violent stretching of spacetime would have generated a background hum of gravitational waves, a permanent imprint from the universe's very first moment of existence. Detecting this signal would be like finding the holy grail of cosmology. Unlike the cosmic microwave background, which shows us the universe at the tender age of 380,000 years, primordial gravitational waves would give us a direct glimpse into a period known as the Planck epoch, a time so early that our current laws of physics break down. It would be a direct messenger from the era where gravity and quantum mechanics were unified, a window into the energy scale of inflation itself. The primary way scientists are hunting for this signal is by looking for its unique fingerprint on the cosmic microwave background. These primordial ripples would have subtly affected the polarization, or the orientation, of the CMB light in a specific, swirling pattern known as a B-mode polarization. Ambitious experiments like the BICEP array at the South Pole are tirelessly scanning the sky, trying to isolate this faint pattern from other interfering signals, like dust within our own galaxy. The implications of a confirmed detection are staggering, as Nobel laureate Kip Thorne has poetically suggested. It would be akin to hearing the universe's first cry. It would provide the most direct evidence yet for the theory of inflation, telling us not just that it happened, but how it happened, revealing the incredible energy involved and pointing us toward the specific physics that drove it. This could finally bridge the gap between the world of the very large, governed by general relativity, and the world of the very small, ruled by quantum mechanics. It might even offer clues about the existence of a multiverse, a concept where our universe is just one bubble in a vast, frothing cosmic ocean of expanding spaces. These space-time vibrations are the faintest echoes imaginable, but they carry the loudest story of all, the story of how everything began. Now, let's turn our attention to one of the most ghostly and pervasive messengers from the dawn of time. Right at this very moment, as you watch this video, you are being traversed by trillions upon trillions of nearly massless particles every single second, passing through your body, your home, and the entire Earth as if they weren't even there. These are neutrinos, and a specific, ancient population of them are direct relics from the universe's first second of existence. Just 1 second after the Big Bang, the cosmos had expanded and cooled sufficiently for these elusive particles to stop interacting frequently with other matter and to begin streaming freely across the universe. This moment, known as neutrino decoupling, created a cosmic neutrino background that has been flowing through everything ever since, a fossil record even older than the cosmic microwave background. This sea of relic neutrinos is often called the ghost population of the cosmos, and for good reason. Their defining characteristic is that they interact with ordinary matter only through the weak nuclear force and gravity, making them incredibly difficult to detect. They are the universe's most elusive spectators, carrying pristine information about the thermal state and conditions of the universe from a time before the first atoms ever formed. While we have detected neutrinos from the Sun, nuclear reactors, and even distant supernova, capturing one of these specific ancient neutrinos is perhaps one of the greatest experimental challenges in all of physics. Their energy is so incredibly low after being stretched by the universe's expansion for over 13 billion years that they simply slip through our most sophisticated detectors unnoticed. This is why projects like the upcoming PTOLEMY experiment are so revolutionary. They are designed to attempt the seemingly impossible, to capture these ghostly particles directly. The experiment plans to use vast arrays of ultra-clean, solid-state detectors, chilled to incredibly low temperatures, hoping that on an exceedingly rare occasion, a relic neutrino will interact with a nucleus and betray its presence. The payoff for such a detection would be monumental. It would open a direct window into the universe's first second, allowing us to study its temperature and expansion rate with unprecedented precision. Furthermore, because the dynamics of these neutrinos are so sensitive to their mass, detecting them would finally allow us to pin down the exact masses of the different neutrino types, a fundamental question in particle physics that remains unresolved. The influence of these relic neutrinos is felt across the cosmos, even if we can't easily detect them individually. In the early universe, their immense numbers and high energy meant they contributed significantly to the overall density of the cosmos, which in turn influenced the rate of expansion. Their tendency to free stream out of dense regions also played a subtle but crucial role in shaping the large-scale structure of the universe. They smoothed out the tiniest density fluctuations, which left a measurable imprint on the pattern of galaxy clusters we see today, and even on the subtle anisotropies in the cosmic microwave background. By studying these patterns, cosmologists can indirectly infer the presence and properties of this cosmic neutrino background. Perhaps most profoundly, as Nobel laureate Arthur MacDonald's work on neutrino oscillations highlighted, understanding neutrinos is intrinsically linked to one of the universe's deepest mysteries, why we exist at all. The standard model of particle physics suggests that the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a universe of pure energy. The fact that we live in a universe dominated by matter implies a fundamental asymmetry, a violation of this symmetry known as charge parity violation. Neutrinos, with their strange properties and ability to oscillate between different states, are prime candidates for having triggered this imbalance in the universe's earliest moments. The secrets locked within these faint, pervasive particles could therefore explain the very origin of everything we see, from the stars above to the atoms within us. But while we are surrounded by these ancient particles, another invisible and pervasive force might also be a direct relic from the universe's infancy, one that weaves through the vast spaces between galaxies and guides the birth of stars: magnetic fields. We are all familiar with magnetism on Earth, from the simple compass needle pointing north to the complex magnets inside our electronics. Out in the cosmos, we observe magnetic fields everywhere we look. They are threaded through galaxies, woven into galaxy clusters, and even detected in the immense voids of empty space between these structures. For a long time, astronomers assumed these fields were generated relatively recently in cosmic history, perhaps by dynamo effects within the first generations of stars and galaxies, where swirling motions of charged particles could amplify a small seed field into the powerful forces we observe. But a more profound and tantalizing possibility exists, that the seeds for these cosmic magnetic fields were not created in galaxies, but were instead planted in the very first instance after the Big Bang, making them truly primordial. The challenge with this idea is that the universe in its earliest, most symmetric state shouldn't have had a preferred direction or a magnetic field. For a magnetic field to be created, you need a process that can break this perfect symmetry, generating a small but persistent imbalance. Theorists have proposed several dramatic scenarios from the universe's first second that could have done exactly this. Perhaps during the violent phase, transitions that occurred as the fundamental forces of nature separated from their initial unified state, like when the electromagnetic and weak forces split, cosmic defects formed, creating tiny currents that generated the first magnetic seeds. Another compelling idea is that during the period of inflation itself, the same quantum fluctuations that seeded galaxies could have also generated fluctuations in electromagnetic fields, leaving behind a faint, imprinted magnetic field that was then stretched to cosmic proportions. Detecting the primordial nature of these fields is incredibly difficult because their original signal is so weak and has been overwritten by later astrophysical processes. However, their ancient origin would leave subtle, unique fingerprints that modern observatories are now hunting for. One key signature would be the presence of a large-scale, coherent magnetic field that permeates the entire cosmos, even in the deepest, emptiest voids where no galaxies have ever formed to create one. Another clue lies in the polarization pattern of the cosmic microwave background. A primordial magnetic field would have affected the polarization of this ancient light in a specific way, and while the Planck satellite has placed tight constraints on this, the search continues with ever more sensitive instruments. Radio telescopes also play a crucial role, as they can measure the magnetic fields in the most distant and ancient gas clouds, looking for signs of a field that existed before the first stars were born. If we could confirm that a significant portion of the universe's magnetism is indeed primordial, it would be a monumental discovery. It would open a brand new window into the physics of the ultra-early universe, providing direct evidence for those first phase transitions or for the intricate details of the inflationary epoch. It would mean that these invisible lines of force have been an integral part of the cosmic story since the very beginning, silently shaping the evolution of the cosmos. They would have guided the collapse of the first gas clouds, influenced the formation of the first stars, and directed the propagation of high-energy cosmic rays across millions of light years. These magnetic fields are not just a later addition to the universe. They could be a fundamental part of its architecture, an invisible cosmic scaffold that has been structuring matter from the first fraction of a second right up to the present day, connecting the moment of creation to the dynamic cosmos we observe now. Now let us turn our attention to the invisible backbone of the cosmos, the hidden architecture that dictates the placement of every galaxy and the vast emptiness between them. If you could see the universe not in light but in gravity, you would witness an immense and intricate cosmic web, a breathtaking tapestry of massive filaments, dense knots, and sprawling, empty voids stretching across billions of light years. This entire grand structure is shaped not by the stars and gas we can see, but by the profound gravitational influence of dark matter, a mysterious substance that outweighs all the ordinary atoms, planets, and stars in the universe by a ratio of 5-to-1. Its gravitational pull is the primary architect of our reality, a force that began sculpting the cosmos from its very first moments. This story starts with the tiny quantum fluctuations imprinted on the universe during the inflationary epoch, those minuscule ripples in space-time that were stretched to cosmic proportions. As the universe expanded and cooled, dark matter, which interacts only through gravity and possibly the weak nuclear force, was the first material to respond to these primordial imperfections. Because it doesn't feel the pressure of radiation that buffeted ordinary particles in the hot, dense early plasma, dark matter could begin to clump together long before normal matter could. Through sophisticated computer simulations based on our prevailing lambda CDM model of cosmology, we can watch this process unfold virtually. We see how dark matter collapsed first into a vast, invisible scaffold, a gravitational skeleton upon which the ordinary, baryonic matter would later be draped. The gas and dust that would eventually form stars and galaxies simply flowed into the gravitational wells carved out by dark matter, following the blueprint it provided. The distribution of galaxies we observe today with powerful telescopes is therefore not random. It is a precise tracery of that underlying dark matter foundation. When projects like the Dark Energy Survey or the upcoming Euclid Space Telescope meticulously map the positions and shapes of billions of galaxies, they are essentially creating a three-dimensional chart of this dark web. They use a technique called gravitational lensing, where the light from distant galaxies is subtly warped and distorted as it passes through the gravitational fields of intervening dark matter clumps. By measuring these tiny distortions, astronomers can literally weigh the unseen matter and reconstruct its distribution across the sky. This allows us to test fundamental theories about what dark matter actually is. Is it made of weakly interacting massive particles or WIMP heavy particles left over from the early universe? Or could it be composed of incredibly light, wave-like actions, or perhaps something even more exotic that would require us to rewrite the laws of physics? Understanding the precise arrangement of dark matter does more than just solve a local mystery of why galaxies rotate the way they do. It provides a direct line of communication back to the universe's initial conditions. The statistical properties of the cosmic web, the sizes of the voids, the thickness of the filaments, the masses of the largest clusters, are a frozen record of the amplitude and nature of those initial quantum seeds from inflation. By studying this large-scale structure, we are effectively conducting archaeology on the first moments of time, testing our models of the very beginning. Furthermore, the evolution of this web over billions of years is intensely sensitive to the other great cosmic mystery, dark energy, which acts to accelerate the expansion of the universe and thus stifles the growth of these vast structures over time. The dark matter we cannot see is perhaps the most eloquent messenger we have, telling us not only about the birth of the cosmos but also whispering hints about its ultimate fate, whether it will continue expanding forever or culminate in some other, more dramatic destiny. Just when we thought we had a handle on the universe's expansion, believing that the gravitational pull of all matter should be gradually slowing it down after the Big Bang, cosmology was turned on its head by a discovery so shocking it earned the Nobel Prize in 2011. In the late 1990s, two independent teams of astronomers, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, were using distant supernova as cosmic mile markers. These specific explosions, type 1 a supernova, act as standard candles because they always explode with roughly the same intrinsic brightness. By carefully measuring how dim they appeared from Earth, the teams could calculate precise distances to galaxies billions of light-years away. Coupled with measurements of how much their light was redshifted stretched by the expansion of the universe, they could chart how the expansion rate has changed over cosmic history. To their absolute astonishment, the data revealed that instead of slowing down, the expansion of the universe is accelerating. It is speeding up. Some mysterious, repulsive force is actively pushing galaxies apart from one another at an ever-increasing rate. This mysterious force was dubbed dark energy, and it is now understood to be the dominant component of our cosmos, making up a staggering 68% of the total energy density of the universe. Its nature is arguably the most profound puzzle in all of modern physics. The leading hypothesis is that dark energy is an intrinsic property of space itself, the energy of the vacuum, often referred to as the cosmological constant, which Einstein initially proposed and then famously discarded as his greatest blunder. In this view, empty space is not truly empty. According to quantum mechanics, it is a seething, bubbling foam of virtual particles constantly popping in and out of existence. This quantum activity endows every cubic centimeter of space with a tiny amount of energy that exerts a negative pressure, a sort of anti-gravity that drives the universe apart. The great enigma is that when physicists try to calculate the expected strength of this vacuum energy using quantum field theory, they arrive at a number that is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is the worst prediction in the history of science, indicating a fundamental gap in our understanding. An alternative possibility is that dark energy is not a constant but a dynamic field that has changed over time, sometimes called quintessence. This would mean the strength of this repulsive force could have been different in the past and might evolve in the future. This is where powerful new tools like the James Webb Space Telescope become indispensable. By peering back to the universe's youth and mapping the distribution of galaxies and the precise timing of the acceleration, JWST, and ground-based observatories like the Vera C. Rubin Observatory are trying to determine the equation of state of dark energy, a key parameter that could distinguish a true cosmological constant from a dynamic quintessence field. The cosmic microwave background also holds vital clues. The precise pattern of fluctuations in the CMB, as measured by the Planck satellite, tells us the total density of the universe and confirms that dark energy must exist to make the geometry of the universe flat, just as inflation predicted. The dialogue between dark energy and gravity is the central battle shaping the ultimate fate of everything. Gravity is the great clumper, the force that pulls matter together to build galaxies, stars, and planets. Dark energy is the great emptier, the force that pushes space itself apart, driving galaxies away from each other and threatening to dilute the universe into a cold, dark, and lonely end. The current evidence suggests that if dark energy is indeed a constant cosmological constant, this battle has a foregone conclusion. The acceleration will continue unabated, leading to a big freeze or heat death, where galaxies beyond our local group eventually move away faster than the speed of light, disappearing from our view forever, and the universe expands into an eternal, cold, and empty void. The discovery of this cosmic acceleration was not just about finding a new component of the universe. It was about uncovering the engine that is driving the entire cosmic story towards its final chapter, forcing us to confront the profound physics of nothingness itself. To understand this next cosmic messenger, we need to journey back to that hot, dense plasma that filled the universe before the cosmic microwave background was released. At this time, the cosmos was a roiling sea of photons, electrons, and atomic nuclei, the particles collectively known as baryons. This soup was not silent, it was alive with sound. But these weren't sound waves as we know them, traveling through air. These were true pressure waves, ripples of density that moved through the primordial fluid at a significant fraction of the speed of light. The engine for these waves was a constant tug of war between two titanic forces, the intense radiation pressure from the searing light, which tried to push matter apart, and the relentless pull of gravity, which tried to pull it all back together. When a region of this plasma became slightly denser due to a random quantum fluctuation, gravity would try to collapse it further, but as matter collapsed in, it would compress the radiation, building up immense pressure that would then blast the material outward in a powerful wave. This matter would then overshoot, creating a slightly underdense region, which gravity would then pull back in, and the cycle would repeat. This created a series of spherical sound waves, like ripples from a stone dropped in a pond, propagating outward from every single initial density fluctuation across the entire universe. This cosmic symphony played on for nearly 400,000 years until the moment of recombination. When electrons and protons combined to form neutral atoms, the universe suddenly became transparent. The photons, the source of the radiation pressure, decoupled from the matter and streamed away as the CMB. Without that outward pressure, the sound waves instantly froze in place. The matter that had been traveling outward in these spherical shells was suddenly stranded, left at a very specific distance from the center of each original fluctuation. This distance, the distance that sound could travel in that nearly 400,000-year period, became a permanent, frozen ruler etched into the fabric of the cosmos. It is known as the sound horizon, and it measures about 500 million light-years across. For billions of years, this pattern lay hidden as gravity continued to work, causing all matter, both the dark matter and the ordinary baryonic matter, to collapse into the intricate cosmic web we see today. But the imprint of those ancient sound waves was not erased. It remained as a subtle statistical preference for galaxies to be separated by that specific scale, the size of the sound horizon. Imagine tossing a handful of pebbles into a still pond and letting the ripples expand and then instantly freeze. If you then came back later and found that most of the leaves floating on the pond's surface were clustered at the peaks of those frozen ripples, you would have detected the Baryon acoustic oscillation signal. This is precisely what massive galaxy mapping projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument are designed to do. They aren't looking at individual galaxies, they are conducting a massive cosmic census, measuring the precise three-dimensional positions of millions of galaxies to see the forest, not the trees. By analyzing this vast map of the universe, they can detect that subtle, preferred clustering scale. Because we know the true, physical size of this standard ruler, that 500 million light-year diameter from the early universe, it becomes an incredibly powerful tool. By measuring how large this ruler appears to be on the sky at different distances from us, and therefore at different eras in cosmic history, we can precisely measure how the universe itself has expanded and stretched over billions of years. This makes BRO one of the cleanest and most robust probes we have for studying dark energy. Unlike supernova, which can have complexities in their explosions, or the CMB, which is a single snapshot from one early time, the Baryon acoustic oscillation provides multiple calibration points throughout history. It allows us to trace the expansion history of the universe with extraordinary precision, testing whether dark energy has remained a constant cosmological constant, or if its strength has varied over time. Furthermore, because this phenomenon is a direct result of the interplay between gravity and radiation pressure in the early plasma, its characteristics are deeply tied to the initial density fluctuations laid down by inflation. The strength of the BRO signal confirms the fundamental nature of those primordial seeds, providing yet another independent line of evidence that points back to our universe's explosive and orderly beginning. This breathtaking idea of exponential expansion solves not just one, but several of the universe's most puzzling mysteries in a single, elegant stroke. The horizon problem, which we explored earlier, asks how regions of the cosmos on opposite sides of the sky could have such a uniform temperature when they were never in causal contact. Without inflation, there simply wasn't enough time for heat or information to travel between them. Inflation provides the perfect answer. Before this rapid expansion, the entire observable universe was once a tiny, infinitesimally small patch that was thoroughly mixed and in thermal equilibrium. Inflation then took that tiny, uniform region and stretched it to a size larger than our entire observable cosmos, preserving that perfect uniformity across vast distances that only later fell out of contact. Similarly, the flatness problem asks why the geometry of our universe is so perfectly balanced between open and closed, a condition that requires incredible fine-tuning of the initial expansion energy. Again, inflation provides the answer. No matter what the initial curvature of that tiny patch of spacetime was, the act of inflating it by such an enormous factor, doubling in size perhaps 100 times or more in a fraction of a second, would have stretched it into apparent flatness, just as inflating a balloon makes any small section of its surface look flatter and flatter. The predictions that inflation makes for the cosmic microwave background are remarkably specific and detailed. It predicts that the tiny temperature fluctuations we see should follow a Gaussian, or random, statistical distribution, which is exactly what we observe. It also predicts that these fluctuations should be nearly scale invariant, meaning that the amplitude of the ripples should be roughly the same across all different size scales, from the largest superclusters down to the tiniest variations. This, too, matches the Planck satellite's data with stunning precision. Most profoundly, this theory gives a tangible, physical origin to the largest structures in the universe. The microscopic quantum fluctuations that are an inherent part of any field, constantly bubbling in and out of existence, would have been caught by the inflationary expansion and stretched from a quantum scale to an astronomical scale. These tiny random ripples in the fabric of spacetime became the density variations that, over billions of years, gravity would amplify into galaxies, clusters, and the entire cosmic web. In this view, the majestic architecture of the cosmos has its roots in the fundamental uncertainty of the quantum world. The quest to confirm inflation is now entering its most exciting phase. While the CMB temperature patterns provide strong circumstantial evidence, the true smoking gun would be the detection of a specific pattern in the polarization of that ancient light, known as primordial B-mode polarization. This unique swirling pattern would be the unmistakable signature of gravitational waves generated during the inflationary epoch itself, ripples in space-time that have been traveling through the universe since its first moment. Ambitious next-generation experiments like CMBS-4, a network of ultra-sensitive telescopes at the South Pole and in Chile, are being designed with the sole purpose of hunting for this faint signal. Finding it would do more than just confirm that inflation happened. It would tell us the energy scale at which it occurred, opening a direct window into physics at energies 1 trillion times higher than what we can achieve at the Large Hadron Collider. It would provide our first real experimental data about the era of grand unification, when the strong, weak, and electromagnetic forces were all one. The implications could extend even beyond our own universe, lending credence to the idea of eternal inflation and a multiverse, a vast, perhaps infinite, ensemble of universes, each with its own unique physical constants and laws, with our own being just one bubble in a frothing cosmic ocean. Confirming inflation would not just complete a chapter in cosmology, it would fundamentally transform our understanding of reality, connecting the quantum mechanics of the incredibly small to the ultimate fate of the entire cosmos. Now, let's descend from the vast scales of cosmic inflation into the deepest, most fundamental layer of reality, the world of particles and forces. To understand the universe's first moments, we must grasp a beautiful and powerful concept: symmetry. In its most pristine, high-energy state, the early universe was a place of perfect symmetry, where the fundamental forces we know today, the strong nuclear force, the weak nuclear force, and electromagnetism, were not separate at all. They were unified into a single, elegant superforce. Particles, too, were massless and indistinguishable, zipping through the searing plasma at the speed of light. But as the cosmos expanded and cooled, it underwent a series of profound metamorphoses, much like water freezing into ice. These critical moments are known as phase transitions, and they shattered that pristine symmetry, giving the universe the rich diversity and structure we see today. The most significant of these transitions for our everyday existence is called electroweak symmetry breaking. This occurred when the universe was just a picosecond old, a trillionth of a second after the Big Bang. At that instant, the temperature dropped below a critical threshold of about 10 to the 15th power Kelvin. In that moment, a field that had been lurking in the vacuum of space everywhere, now known as the Higgs field, suddenly switched on. Imagine this field as a kind of cosmic molasses that uniformly fills all of space. Before the transition, particles like electrons and quarks were massless, moving at light speed. But as the Higgs field activated, certain particles began to interact with it, trudging through this molasses and thereby acquiring the property we call mass. This mechanism, confirmed spectacularly by the discovery of the Higgs boson at the Large Hadron Collider in 2012, is what allows matter to clump together. Without it, there would be no atoms, no planets, no stars, and certainly no us. The Higgs boson itself is a ripple in that field, a direct messenger from that first picosecond, and studying its properties tells us about the precise conditions of that epochal break. Theoretical physicists believe that even earlier phase transitions occurred, at energies so high we can only dream of recreating them. These would have been moments when the strong force split off from the electroweak force, or perhaps when all forces were truly one in a state of grand unification. Such cataclysmic events might have left behind permanent scars in the fabric of spacetime fossils known as topological defects. One of the most sought after of these relics is the magnetic monopole. In our everyday world, magnets always have two poles. You can't have a north without a south. But theories of grand unification predict that in the ultra-early universe, isolated north and south magnetic poles, or monopoles, should have been created in abundance during these symmetry breaking phase transitions. They would be incredibly massive, stable particles, and if even a few survived from the beginning, they should still be drifting through the cosmos today. Decades of searching in everything from moon rocks to deep sea deposits have yet to find one, but their discovery would be a direct ticket to understanding physics at energies a quadrillion times greater than the LHC can achieve. This is the ultimate goal of particle colliders like the LHC, to turn back the cosmic clock. By smashing protons together at velocities approaching the speed of light, we recreate, for a fleeting instant in a microscopic volume, the unimaginable temperatures and densities of the universe's first trillionth of a second. We are not just hunting for the Higgs, we are probing for any sign of new physics that could explain the great mysteries that the standard model leaves unanswered. Why is there such a staggering hierarchy between the weakness of gravity and the strength of the other forces? Could the particles that make up dark matter be produced in these collisions, revealing themselves in the detectors? Do neutrinos get their tiny mass from the Higgs field or from some other, more exotic mechanism? Every time the LHC conducts a new run at higher energies, we are essentially tuning into an earlier and earlier cosmic broadcast, listening for whispers of the universe's unified past. The very fact that we have distinct forces and a zoo of particles with different masses is not a flaw. It is a frozen historical record, a snapshot of the sequential breaking of symmetries that turned a featureless, symmetric fireball into the complex and habitable cosmos we call home. It's one of the most fascinating twists in the history of science, a concept introduced out of necessity, famously rejected as an error, only to be spectacularly resurrected decades later to explain one of the greatest discoveries of all time. This is the story of the cosmological constant, often referred to as Einstein's biggest blunder. In 1917, when Einstein was applying his new theory of general relativity to the entire cosmos, the prevailing astronomical belief was that the universe was static, eternal, and unchanging. But his equations told a different story. They predicted that a universe filled with matter should either be expanding or contracting under gravity's relentless pull. Unwilling to challenge the scientific consensus of a static cosmos, Einstein made a slight modification to his own beautiful equations. He added a new term represented by the Greek letter lambda, which represented a kind of repulsive force, a negative pressure that would perfectly balance the attractive force of gravity on the largest scales, thereby achieving the static universe everyone thought they lived in. More than a decade later, when Edwin Hubble's observations of receding galaxies confirmed that the universe was indeed expanding, Einstein reportedly discarded the cosmological constant with regret, calling it his greatest mistake. For most of the 20th century, that's where the story ended. Lambda was a historical footnote, a cautionary tale about not doubting your own mathematics. But the story wasn't over. In the late 1990s, as we discussed, astronomers discovered that the universe's expansion wasn't just continuing, it was accelerating. Something was pushing galaxies apart faster and faster. Theorists quickly realized that the perfect candidate for this mysterious repulsive force had been hiding in plain sight all along, written into the very fabric of Einstein's equations. The cosmological constant was back not as a mistake but as the leading explanation for dark energy. It was reinterpreted not as a balancing force but as an inherent property of space itself, the energy of the vacuum. This is where the story goes from fascinating to deeply mysterious. According to quantum mechanics, the vacuum of space is not empty. It is a seething, bubbling foam of virtual particles that constantly pop into and out of existence, a phenomenon known as quantum fluctuations. Every theoretical attempt to calculate the energy density of this quantum vacuum leads to a number, but that number is catastrophically, inexplicably wrong. The predicted value is about 10 to the power of 120 times larger than the value we actually observe from cosmological measurements. This is not a small error. It is the largest discrepancy between theory and observation in all of science. If the vacuum energy were anywhere near as strong as quantum field theory suggests, the repulsive force would have been so immense that it would have ripped apart every atom, star, and galaxy before any of them could ever have formed. The universe would be a featureless, accelerating void. The fact that we exist to observe a universe with structure means the value must be incredibly small, but not zero. This fine-tuning is so precise it borders on the unbelievable, leading physicists to wonder if this is just a staggering coincidence or if there is a deeper principle at work that we have yet to understand. This enigma bridges the two great pillars of modern physics, the cosmic and the quantum, in the most uncomfortable way possible. General relativity describes the universe on the largest scales with incredible accuracy, while quantum mechanics does the same for the subatomic world. Yet when we try to combine them to understand the energy of empty space, we get this nonsensical result. Solving this problem is perhaps the central goal of any theory of quantum gravity. The cosmological constant problem forces us to ask profound questions about the nature of reality itself. Is the value of lambda set by the initial conditions of the Big Bang a fundamental constant woven into the laws of physics from the very beginning? Or does its value vary across a vast multiverse, a sprawling collection of universes each with their own unique physical constants? In this anthropic view, we find ourselves in one of the rare, life-permitting universes where the cosmological constant is small enough to allow galaxies and planets to form. This idea is both compelling and controversial, as it leans towards a philosophical explanation rather than a purely predictive physical one. Modern cosmology is actively testing the nature of this enigmatic constant. By measuring the universe's acceleration with ever greater precision using distant supernova, Baryon acoustic oscillations, and the cosmic microwave background, scientists are trying to determine if dark energy is truly a constant cosmological constant, or if its strength has changed over billions of years. A dynamic dark energy, sometimes called quintessence, would show a slight evolution in its equation of state, pointing toward new physics beyond Einstein's original concept. The James Webb Space Telescope and next-generation sky surveys like the Vera-C, Rubin Observatory are at the forefront of this detective work, charting the expansion history of the cosmos with unprecedented detail. The answer will determine the ultimate fate of everything. A true constant means acceleration continues forever, leading to a cold, dark, and lonely Big Freeze. A dynamic constant could suggest a different future, perhaps even a dramatic reversal. The cosmological constant, once thought to be a blunder, is now our best guide to understanding why the universe is the way it is and what its final destiny will be. Now, let's ponder one of the most perplexing puzzles that cosmologists faced before the theory of inflation came along, a conundrum so fundamental it's known as the horizon problem. Gaze out into the deep universe in any direction, and you'll find that the cosmos is remarkably, almost unnervingly, uniform. The temperature of the cosmic microwave background, for instance, is the same everywhere we look, to an astonishing precision of about 1 part in 100,000. Whether we point our telescopes north, south, east, or west, that faint afterglow from the Big Bang has a nearly identical temperature of 2.7 degrees above absolute zero. This incredible large-scale homogeneity is a fundamental feature of our universe. but it also presents a deep paradox rooted in the very nature of causality and the speed of light. According to the laws of physics, no information or influence can travel faster than light. This universal speed limit isn't just a rule for particles, it defines the very boundaries of cause and effect. For two regions of space to have the same temperature, they must have been in thermal contact at some point in the past. They needed to have exchanged energy to reach a common equilibrium. But if we take the standard Big Bang model without inflation and run the clock back, we find a glaring issue. The universe simply hasn't existed long enough for light to have traveled between these vastly separated regions. For example, a point in the sky directly overhead and a point on the opposite side of the sky are separated by a distance so vast that light has had 13.8 billion years to travel between them. Yet the calculations show that these 2 points on the cosmic microwave background have been out of causal contact for the entire history of the universe. There hasn't been enough time for any signal, moving at the speed of light, to have traveled from one to the other to synchronize their properties. It would be like walking into two identical, perfectly synchronized bakeries on opposite sides of the planet and discovering they've never communicated with each other or shared a common recipe. How could they possibly be the same? This is the essence of the horizon problem. The universe appears to be uniform in places that could never have communicated, defying our basic understanding of how physics works. The most widely accepted and elegant solution to this riddle is the theory of cosmic inflation. This idea posits that in the very first fraction of a second, the entire observable universe was once crammed into a region smaller than a single proton. This tiny volume was so incredibly small that every part of it was in direct, intimate causal contact. Heat and information could zip across it instantly, allowing it to smooth out into a state of perfect thermal equilibrium, achieving a uniform temperature and density. Then inflation struck, a period of hyper-fast exponential expansion. In less than a trillionth of a trillionth of a trillionth of a second, that tiny, connected, uniform patch was stretched by a factor of at least 10 to the power of 26, becoming far larger than our entire observable universe today. What we see as opposite ends of the cosmos were once neighboring points, thoroughly mixed and uniform before this incredible stretch. Inflation took that initial uniformity and magnified it to cosmic proportions, explaining why the universe looks the same in all directions even though those regions have been out of touch ever since. While inflation is the leading solution, it's important to note that a few alternative ideas have been proposed, though they are far less mainstream. Some physicists have explored theories where the speed of light itself was not a constant in the early universe. In these variable speed of light, or VSL, scenarios, light could have traveled much, much faster in the extreme heat of the Big Bang, allowing it to connect these distant horizons and create uniformity before settling down to the constant speed we measure today. However, these theories often require radical modifications to well-tested physics and lack the same breadth of supporting evidence that inflation has accumulated. The stunning uniformity of the CMB, therefore, isn't just a curious fact. It's powerful evidence that our observable universe did indeed emerge from a tiny, causally connected region. It forces us to consider that the initial conditions of the cosmos were not random and chaotic, but were instead set up with a very specific, very smooth configuration that has been preserved and amplified over billions of years. Resolving the horizon problem does more than just fix a cosmological headache. It profoundly deepens our understanding of causality and the limits of physical law in the primordial universe. It suggests that the principle of causality, so sacred to our everyday experience, had its boundaries redrawn in that first fleeting instant. The regions we see today were only able to communicate because the rules of the game were different at the very beginning. This large-scale uniformity implies that the initial state of the universe was one of incredible order and simplicity, a blank canvas upon which the complex structures of galaxies and clusters would later be painted by the gentle hand of gravity. It points toward a beginning that was far from arbitrary, hinting at a fundamental mechanism like inflation that set the stage for everything to come. This incredible geometric precision of our universe is one of its most deeply puzzling features. Imagine balancing a pencil perfectly on its sharpened tip. In theory, it's possible, but the slightest breath of air, the tiniest vibration, would send it toppling over. It is an exquisitely unstable equilibrium. Now, apply that same idea to the entire cosmos. The fate of the universe is governed by a simple cosmic tug of war between two opposing forces: the outward momentum of the Big Bang's expansion, which drives galaxies apart, and the inward pull of gravity, which tries to pull everything back together. The balance between these two titanic forces is described by a number cosmologists call omega. If omega were greater than 1, meaning the density of matter and energy was high enough for gravity to win, the universe would eventually stop expanding and collapse back in on itself in a fiery, big crunch. If omega were less than 1, the density would be too low, and the universe would expand and dilute forever into a cold, empty, big freeze. The astonishing reality, confirmed with ever-increasing precision by measurements of the cosmic microwave background and the Baryon acoustic oscillations, is that omega is almost exactly 1. The universe is geometrically flat. Not flat like a sheet of paper, but flat in the sense of Einstein's general relativity, meaning the rules of Euclidean geometry we learned in school hold true on the largest scales. The angles of a giant cosmic triangle would add up to exactly 180 degrees. This isn't just a close call. Observations from the Planck satellite show that the density of the universe is within just 0.4% of the critical value needed for flatness. To have such a perfect balance today, some 13.8 billion years after the Big Bang, the initial conditions had to be fine-tuned to an almost unimaginable degree. In the first second of the universe, the density must have been precisely 1 to within 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. To put that number in perspective, it is vastly more precise than balancing that pencil on its tip for billions of years. Without a mechanism to explain this, such a perfect setup seems like an impossible, wildly improbable coincidence. This is the flatness problem, and like the horizon problem, it finds its most compelling solution in the theory of cosmic inflation. The genius of inflation is that it acts like a cosmic iron, smoothing out any initial curvature the universe might have had. Think of the surface of a balloon. When it's only partially inflated, you can see all sorts of wrinkles and curves on its surface. But as you blow it up to a much larger size, any small section of that balloon's surface appears flatter and flatter. Inflation proposes that our entire observable universe was once a tiny, perhaps highly wrinkled patch of space. That patch then underwent an exponential expansion, doubling in size over and over again in a fraction of a second. This incredible stretching would have flattened the geometry of that local region, just as inflating the balloon flattens its surface. By the time inflation ended, that tiny patch, now enormous and perfectly flat, became the seed for our entire observable cosmos. The flatness we measure today isn't a mysterious initial condition. It's a direct prediction and a natural consequence of this rapid stretching. This profound fine-tuning inevitably pushes our thinking into the realm of philosophy and deeper physics. It challenges our notion of naturalness, the idea that the fundamental parameters of the universe should be of order 1 and not require incredible precision to allow for a habitable world. The flatness problem suggests that the initial state of the universe was anything but natural. It was bizarrely, specifically configured. This has led some physicists to consider the anthropic principle. In this view, perhaps there is not one universe, but a vast multiverse, an endless landscape of universes, each with different physical constants and initial densities. In the overwhelming majority of these universes, omega is not one. They either collapse immediately or expand into utter emptiness, never forming galaxies, stars, or planets. We find ourselves in a flat universe not because it's likely, but because it's the only type of universe that can support conscious life forms like us who can ask the question. While this is a compelling way to approach the problem, it remains deeply controversial because it leans on a selection effect rather than a predictive physical theory. The flatness of space is therefore more than a geometric curiosity. It is a fundamental clue about the origin of everything, pointing either to a specific physical mechanism like inflation or to a much broader and stranger cosmic reality. Contemplate the very moment of the Big Bang, the ultimate beginning as we understand it. For decades, the standard cosmological model has pointed back to a single, unimaginable point, a singularity of infinite density and infinite temperature, where all the mass and energy of the entire cosmos was compressed into a volume of zero size. At this point, the equations of Einstein's general relativity, which so beautifully describe the curvature of space-time and the force of gravity, simply break down. They return results that are nonsensical infinities that signal our mathematical tools have hit their limit. This singularity is not just a physical object. It is the ultimate boundary of our knowledge, a place where the known laws of physics cease to apply, desperately beckoning for a deeper theory that can unite gravity with the quantum world. While we can never directly observe this singularity, its profound shadow is cast across the entire universe we see today. The expanding cosmos itself is the primary clue, the direct aftermath of that initial event. The precise patterns in the cosmic microwave background, the very same ripples that grew into galaxies, are the echo of the universe's first breath, carrying imprints of the conditions that emerged from the singularity's immediate wake. Furthermore, the hunt for primordial gravitational waves is essentially a search for vibrations that originated when the universe was perhaps only a trillionth of a trillionth of a trillionth of a second old, potentially giving us an indirect glimpse into the physics that took over at the moment the singularity would have existed. Because the classical concept of a singularity is so problematic, modern physics has begun to propose compelling alternatives that seek to avoid this infinite breakdown. Theories like loop quantum gravity, for instance, suggest that due to quantum effects, gravity becomes repulsive at extremely high densities. This would mean the universe did not emerge from a point of infinite density, but instead from a prior, contracting phase that bounced into our current expansion. In this cosmic bounce scenario, our Big Bang was not the absolute beginning, but rather a transformative rebirth from a previous universe that had collapsed. String theory, another candidate for a theory of everything, also allows for possibilities that avoid a true singularity, including ideas of a cyclical universe or a multiverse where our cosmos is one bubble among many in a greater, eternal quantum foam. Each of these theories could leave its own unique, detectable signature, a specific pattern in the gravitational wave background or a subtle deviation in the CMB polarization that future experiments might one day uncover. Understanding the true nature of this initial point or its absence is the fundamental key to unlocking the greatest unification in physics, merging the world of the very large, governed by general relativity, with the world of the very small, ruled by quantum mechanics. A theory of quantum gravity is required to describe these first moments, and in doing so, it would not just tell us how our universe began, but would potentially reveal the true origin of time, space, and existence itself. The implications are staggering to consider. If the initial singularity is replaced by a bounce or another mechanism, it suggests that time itself may not have had a beginning. Our universe's history could extend back indefinitely, forever beyond our observational horizon. The absence of a true beginning point would transform our philosophical and scientific understanding of reality, moving from a single, creationary event to a potentially eternal cycle of transformation, where the cosmos has always existed in some form, forever renewing itself according to a deeper, more fundamental set of physical laws. But what if the grand cosmic architecture we see today, the sprawling galaxies, the glittering stars, the very planets we call home, all originated from the tiniest, most random whispers of the quantum world? This is the profound revelation behind quantum fluctuations. At the heart of quantum mechanics lies a fundamental and strange principle, Heisenberg's uncertainty principle. It tells us that on the smallest scales, empty space is not truly empty. It is a seething, bubbling sea of potentiality, where pairs of virtual particles and antiparticles constantly pop into and out of existence, borrowing energy from the vacuum for an infinitesimally brief moment before annihilating each other and returning it. This is not a theoretical curiosity, it's a proven phenomenon with measurable effects like the Casimir force. In our everyday world, these quantum jitters are utterly negligible, confined to a realm far smaller than an atom. But in the first fraction of a second after the Big Bang, the universe provided a mechanism to take these microscopic, random events and magnify them to a cosmic scale: inflation. The theory of cosmic inflation proposes that the universe underwent a period of exponentially rapid expansion, growing by a factor of trillions upon trillions in a tiny fraction of a second. As this incredible stretching occurred, it acted upon those minuscule quantum fluctuations in the fabric of spacetime itself. Imagine drawing a tiny, random squiggle on a deflated balloon. Now imagine inflating that balloon to the size of the Earth. That once tiny, insignificant squiggle is now a massive, mountainous ridge spanning continents. Inflation did exactly this. It took those random quantum ripples, tiny variations in density, and stretched them across the entire cosmos, freezing them into the primordial plasma as regions that were ever so slightly denser or less dense than their surroundings. These became the gravitational seeds for all future structure. Without this quantum randomness, the initial conditions of the universe would have been perfectly smooth, and without any density variations, gravity would have had nothing to grab onto. The universe would have remained a forever barren, uniform, and lifeless soup of hydrogen and helium, expanding into eternal darkness. The evidence for this incredible story is written across the sky in the cosmic microwave background. The subtle anisotropies, those tiny variations in temperature of just a few millionths of a degree, are the direct imprint of those amplified quantum fluctuations. They represent the blueprints from which the cosmic web was built. By studying the statistical properties of these temperature variations with exquisite precision, using satellites like Planck, cosmologists can perform a powerful test of the inflationary paradigm. The theory makes a very specific prediction that these primordial fluctuations should be nearly scale invariant and follow a Gaussian or random statistical distribution. This is exactly what we observe. The patterns in the CMB align beautifully with the idea that the seeds of galaxies were born from quantum noise. The hunt is now on for even subtler signatures that could reveal new physics. Researchers are searching for tiny deviations from perfect Gaussian randomness, features known as non-Gaussianities. Finding them would be like discovering a unique fingerprint in the quantum noise, potentially pointing toward the specific particle physics that drove inflation itself. It could tell us if the inflattened field was a simple single field or something more complex, interacting with other fields in ways that left a faint but detectable trace. This endeavor pushes the boundaries of our understanding, seeking to connect the world of the ultra-small, governed by quantum mechanics, with the world of the ultra-large, described by general relativity. As Nobel laureate Jim Peebles so eloquently put it, these quantum seeds are the reason we exist. They are the ultimate source of all structure, the random quantum dice roll that made the universe interesting, diverse, and ultimately habitable. The fact that we are here to contemplate the stars is a direct consequence of subatomic uncertainty writ large across the cosmos, a breathtaking bridge between the quantum froth and the grand celestial tapestry. After the universe's initial fiery birth and its transition into a transparent, expanding space filled with neutral hydrogen, it entered a profound and silent chapter known as the Cosmic Dark Ages. For millions of years, no stars shone, no galaxies glittered. The cosmos was a vast, dark sea of primordial gas, slowly cooling and condensing under the gentle pull of gravity. Then, somewhere in the darkness, a profound transition began. Enormous clouds of hydrogen, seeded by those ancient density fluctuations from the Big Bang, finally grew dense enough to ignite nuclear fusion in their cores. The first stars were born. These weren't like the stars we see today. They were behemoths, often hundreds of times more massive than our sun, burning ferociously hot and brilliant blue, and living short, violent lives. Their intense ultraviolet radiation began to flood the surrounding space, and this light carried enough energy to rip electrons away from the neutral hydrogen atoms that filled the universe, kicking off a pivotal cosmic event, the epoch of reionization. This process, which unfolded between roughly 150 million and 1 billion years after the Big Bang, was the universe's second great transformation. The first was recombination, when the universe cooled enough to form stable atoms and became transparent. Reionization was, in a sense, the opposite. The first luminous objects, those massive population, 3 stars, early galaxies, and voracious black holes beginning to feast on matter, acted as cosmic lighthouses, their powerful UV emission breaking the neutral hydrogen back apart into a plasma of free electrons and protons. Unlike the initial fog of the early universe, this new plasma was much more diffuse. The electrons were too far apart to efficiently recapture the photons, so the universe did not become opaque again. Instead, it was permanently reionized, becoming the clear and transparent intergalactic medium we observe between galaxies today. This was the universe's adolescence, a turbulent and formative era that ended the Dark Ages and set the stage for the rich cosmic landscape that would follow. How do we possibly study an era that concluded over 12 billion years ago? Astronomers are incredibly clever detectives, using 2 primary methods to trace this ancient transition. The first involves using the most distant and brilliant beacons in the universe, quasars. These are supermassive black holes at the centers of early galaxies, glowing intensely as they consume vast amounts of gas. Their light travels across the cosmos to reach our telescopes. Along its billion-light-year journey, that light passes through clouds of intergalactic hydrogen. If that hydrogen is neutral, it will absorb specific wavelengths of the quasar's light, creating a distinct pattern of dark lines in the spectrum known as the Lyman alpha forest. However, for the most distant quasars whose light was emitted during the reionization era itself, something fascinating happens. At a certain point, a broad swath of absorption appears, completely blocking the light blueward of the Lyman alpha line. This is called the Gunn-Peterson trough, and it is the telltale signature of a universe still filled with significant amounts of neutral hydrogen. By studying quasars at different distances, we can see this trough appear and then gradually fade, creating a timeline of how reionization progressed. The second major clue is imprinted on the cosmic microwave background. As the CMB photons traveled through the newly ionized plasma during the reionization era, a small fraction of them scattered off the free electrons. This scattering left a specific, subtle mark on the polarization of the ancient light. By meticulously mapping the polarization of the CMB across the entire sky, satellites like Planck have been able to measure the total optical depth caused by this scattering. This measurement tells us the approximate time when most of the reionization occurred, pinning it to a mean redshift of around Z equals 7.8, or about 500 million years after the Big Bang. It suggests that reionization was not an instantaneous flash but a protracted process, likely beginning with isolated bubbles of ionized gas forming around the very first stellar clusters before these bubbles eventually grew, overlapped, and filled the entire universe with ionizing radiation. This is precisely where the James Webb Space Telescope is revolutionizing our understanding. JWST is our ultimate time machine, designed to peer directly into this epoch and see the actors responsible for this great transformation. It is discovering and characterizing the very first galaxies, revealing that they were often more numerous, brighter, and more efficient at forming stars than many models had predicted. Some of these early galaxies appear to be producing and leaking copious amounts of ionizing photons, suggesting they were powerful drivers of reionization. Furthermore, JWST is providing clues about the nature of the first stars themselves. While we haven't directly observed a lone population Roman III star yet, the telescope is analyzing the chemical composition of incredibly ancient galaxies. Finding systems almost completely devoid of heavy elements would be strong indirect evidence that they are being lit by this first generation of stars, which lived and died without polluting their surroundings with the products of their fusion. The data from JWST is helping us move from a theoretical understanding of reionization to a detailed historical record, showing us how the first structures emerged to flood the cosmos with light and end the universe's long, dark night. Emerging from the cosmic dark ages, the universe prepared for its first act of true creation. Before this moment, the cosmos was a vast, simple expanse of hydrogen and helium, the pristine elements forged in the Big Bang's first 3 minutes. There were no planets, no complex molecules, and certainly no ingredients for life. The stage was set, waiting for its first performers to ignite. These were the population 3 stars, the universe's inaugural generation of stellar giants. Unlike the stars we see today, these pioneers were born from a pure, untainted gas cloud, composed solely of the 2 lightest elements. This lack of heavier elements, which in later stars helped to cool gas clouds and regulate their collapse, had a dramatic consequence. Without them, the first gas clouds could collapse into truly monstrous structures, giving birth to stars of staggering scale, behemoths thought to be hundreds of times more massive than our own sun. The life of a population 3 star was a spectacular, high-stakes drama played out on a cosmic scale. Their immense mass generated titanic gravitational pressure in their cores, driving nuclear fusion at a ferocious, unsustainable rate. They burned unimaginably hot, shining with a brilliant, blistering blue-white light that was millions of times more intense than our suns, and they lived lives of breathtaking brevity. Where a star like our sun will burn steadily for billions of years, these primal giants exhausted their nuclear fuel in just a few million years, a mere cosmic blink of an eye. Their spectacular deaths were as consequential as their births. When their cores could no longer support their own immense weight, they did not fade quietly. They detonated in cataclysmic supernova of unprecedented power, or in some cases may have collapsed directly into black holes without a traditional explosion. In their final, violent moments, these stars became the universe's first true alchemists. The intense heat and pressure of their lives and deaths fused the primordial hydrogen and helium into the first heavier elements: carbon, oxygen, nitrogen, and iron, the very building blocks of planets and ultimately life itself. We have never directly observed a population 3 star. Their lives were too short, shining in a universe that was still too primordial for our telescopes to easily peer into. Yet we are certain of their existence because we see their indelible signature everywhere we look. The evidence is written in the chemical composition of the oldest stars we can find. In the halo of our own Milky Way galaxy, there exist ancient metal-poor stars known as population 2 stars. By analyzing their light with spectroscopy, astronomers find they contain trace amounts of heavier elements, but not the full range we see in younger stars like our Sun. This tells a clear story. These ancient stars formed from gas clouds that had been seeded by the supernova of just a few prior population 3 stars. They are the second generation, carrying the chemical fingerprint of the first. Furthermore, sophisticated computer simulations of the early universe consistently show that the first structures to collapse under gravity would naturally form these incredibly massive stars, powerfully confirming our theoretical models. The legacy of these stellar pioneers is not confined to the distant past. It is woven into the fabric of our own existence. Every atom of oxygen we breathe, every particle of carbon that forms the basis of our DNA, every trace of iron in our blood was forged in the heart of a star that lived and died long before our Sun was even a glimmer in a nebula. The first population 3 stars began this process, creating the initial heavy elements that polluted the pristine cosmic gas. When subsequent generations of stars formed from this enriched material, they continued the process, creating even heavier elements. Their supernova did more than just create new elements, they sculpted the cosmos. The shock waves from these explosions compressed nearby gas clouds, triggering the formation of the next wave of stars and helping to assemble the first proto-galaxies. And in their spectacular deaths, some of these first stars may have left behind another profound cosmic mystery: the seeds of the supermassive black holes that now lurk at the centers of nearly every galaxy, including our own. Their immense mass could have allowed them to collapse directly into black holes of hundreds or even thousands of solar masses, which then grew over billions of years by consuming gas and merging with others. The echoes of these first brilliant giants resonate through time, in the chemistry of our bodies and the very architecture of the galaxies that dot the night sky. Now let's pull our perspective back to the grandest scale imaginable and witness the ultimate result of all these primordial processes, the magnificent cosmic web. If you could take a journey across the universe, flying past local stars, through our Milky Way galaxy, and out into the depths of intergalactic space, you would eventually witness a structure so vast it defies human comprehension. This is not a random scattering of islands in a dark sea. It is an intricate, organized architecture. Picture an immense sponge or a neural network drawn on a canvas billions of light years across. Glowing filaments of thousands of galaxies twist and connect, meeting at dense, brilliant knots where immense galaxy clusters swarm with trillions of stars. Between these structures lie the cosmic void's caverns of profound emptiness, so vast that a beam of light would take hundreds of millions of years to cross them, containing little more than a few lonely dwarf galaxies adrift in the darkness. This is the large-scale structure of the universe, and it is the direct, grown-up version of the tiny quantum ripples imprinted during inflation. Mapping this colossal architecture is one of the great observational endeavors of modern cosmology. Projects like the Sloan Digital Sky Survey have spent decades meticulously cataloging the positions of hundreds of millions of galaxies across a significant fraction of the observable universe. This isn't just about creating a pretty picture, it's about collecting the data for a massive cosmic census. By precisely measuring the three-dimensional locations of these galaxies, astronomers can perform a statistical analysis of the universe's skeleton. They can measure the average distance between galaxy clusters, the typical size of the voids, and the thickness of the filaments. These measurements are then compared against supercomputer simulations that model the evolution of the universe based on our standard cosmological model, known as lambda cold dark matter. The stunning agreement between the simulated universe and the observed data is one of the strongest validations of our entire cosmic story, confirming the roles of both dark matter as the gravitational scaffolding and dark energy as the agent shaping the expansion. This galactic distribution is far more than a static map. It is a dynamic fossil record. Each galaxy's position tells a story of gravitational attraction over billions of years. The dense clusters are regions where the initial density fluctuations from the Big Bang were strongest, places where dark matter first pooled and drew in ordinary matter. The vast voids are the underdense regions from which matter has slowly drained away over cosmic time, like water flowing from a valley into a growing mountain range. By studying the precise statistical properties of this web, how clustered the galaxies are, the power spectrum of these clusters, cosmologists can work backwards. They can decipher the amplitude and nature of those initial quantum fluctuations, testing the predictions of different inflationary models. They can also trace how the web has been stretched and distorted by the universe's expansion, providing an independent measure of dark energy's influence. The architecture of the cosmos is therefore a history book, its chapters written in the language of gravity, its pages spanning billions of light years, revealing secrets about its own explosive birth and its accelerating fate. This grand tapestry, woven from the threads of dark matter and illuminated by the lights of billions of galaxies, is the ultimate expression of order emerging from chaos, a structure whose blueprints were drawn in the first trillionth of a second of time. But what if some of the most mysterious objects in the cosmos, black holes, did not require the death of a star to be born? Imagine a black hole forming not from a stellar collapse, but directly from the raw, churning energy of the universe's first second. This is the compelling hypothesis of primordial black holes. In the incredibly dense and turbulent environment just moments after the Big Bang, before any stars or galaxies even existed, extreme density fluctuations in the expanding fabric of spacetime could have caused regions to become so overwhelmingly dense that they collapsed directly under their own gravity, pinching off to form black holes. These wouldn't be the stellar mass black holes we know from LIGO observations or the supermassive giants at galactic centers. They could be any size, from smaller than a proton to many times the mass of our Sun, with their size determined by the specific moment in the early universe when that patch of space crossed the critical density threshold. The existence of such ancient objects would be nothing short of revolutionary, offering elegant solutions to two of cosmology's greatest puzzles. First, they are a compelling candidate for dark matter. If vast numbers of primordial black holes were forged in the first instant, and if their mass distribution is just right, they could constitute the invisible mass that holds galaxies together and shapes the cosmic web, all without the need for exotic new particles like WIMP or actions. Second, they could solve the mystery of how supermassive black holes, which weigh millions or even billions of solar masses, appeared so early in the universe's history. It is incredibly difficult for standard stellar collapse to create such behemoths in the short time available after the Big Bang. But if massive primordial black holes were already present, they would have been ready-made seeds, providing a massive head start for these monsters to grow by accreting gas and merging with others. The hunt for these ghostly relics is on, and astronomers are using incredibly clever methods to try and find them. One primary technique is gravitational microlensing. If a primordial black hole were to pass directly between Earth and a distant star, its immense gravity would act like a lens, bending the star's light and causing it to temporarily brighten in a very specific, predictable way. Surveys like the optical gravitational lensing experiment monitor hundreds of millions of stars in nearby galaxies like the Large Magellanic Cloud, watching for these telltale flashes. So far, they have ruled out primordial black holes making up all of dark matter across a wide range of masses, but specific windows remain open. Another method involves listening for their final moments. Stephen Hawking theorized that black holes should slowly evaporate by emitting radiation, a process that would become explosive for very small black holes as they near the end of their lives. We could potentially detect the final, high-energy burst of this evaporation as a flash of gamma rays, a signature of a tiny, dying black hole from the dawn of time. Perhaps the most exciting modern avenue is through gravitational wave astronomy. The LIGO and Virgo observatories have now detected numerous mergers of black holes. While most of these are consistent with black holes formed from stellar evolution, the existence of primordial black holes remains a plausible explanation for some events, particularly those with unusual masses or spins that don't fit neatly into stellar models. If a future detection were to find a black hole with a mass that is simply impossible for a star to produce, or a merger that occurred so early in the universe that stars couldn't have formed and died yet, it would be powerful, albeit indirect, evidence for a primordial origin. Finding these ancient objects would do more than just check a box on a cosmological list. It would provide a direct probe of the physics operating at the highest energies imaginable, moments after the Big Bang. It would tell us about the spectrum of density fluctuations in that primordial chaos, offering a new window into an era that is otherwise completely inaccessible, forever reshaping our understanding of how the cosmos built its most enigmatic structures. To truly listen to the universe's earliest moments, we must sometimes look down at our own planet, to the ancient rocks that have fallen from the sky. Meteorites, particularly a type known as carbonaceous chondrites, are more than just space debris. They are pristine time capsules, frozen relics from the solar system's formation over 4.5 billion years ago that have remained largely untouched by geological processes. Within them, locked in their crystalline structures, are atoms that were forged not in our sun, but in the cataclysmic deaths of stars that lived and died long before our solar system even existed. By meticulously analyzing the ratios of different isotopes within these stones, variants of elements with the same number of protons but different numbers of neutrons, we gain access to a pristine record of the galaxy's chemical composition before our sun stirred it all together. These isotopic abundances are a form of cosmic forensic evidence, providing some of the most stringent tests for our models of the Big Bang and the life cycles of the very first stars. The power of this method is brilliantly illustrated by the case of deuterium, a heavy isotope of hydrogen. During the universe's first 3 minutes, Big Bang nucleosynthesis produced a specific, predicted amount of deuterium. This delicate nucleus is easily destroyed in the hot interiors of stars. It's a fuel that gets burned up. Therefore, by measuring the amount of deuterium in the most primordial, unprocessed gas clouds we can find often by observing the absorption lines they create in the light of incredibly distant quasars, we are essentially measuring the original deuterium abundance left over from the Big Bang. The observed value matches the theoretical prediction with breathtaking precision, but only if the density of ordinary matter, or baryons, in the universe is set to a very specific value. This measurement is so precise that it has become one of the golden constraints of cosmology, pinning down the amount of normal atoms in the cosmos with an uncertainty of less than 1%. It tells us unequivocally that the familiar matter making up stars, planets, and us constitutes only about 5% of the universe's total content, a fundamental pillar in our understanding of the cosmic inventory that points directly toward the dominance of dark matter and dark energy. Yet, not all the elemental evidence lines up so neatly. Lithium presents a particularly stubborn puzzle. Our most sophisticated models of Big Bang nucleosynthesis, which so perfectly predict the amounts of hydrogen, helium, and deuterium, also predict a specific abundance of lithium-7. However, when we look at the oldest stars in the halo of our galaxy, stars that formed from nearly pristine gas and should preserve that primordial lithium, we find only about a third to half the expected amount. This lithium problem has persisted for decades, nagging at cosmologists and hinting that our understanding of the early universe is still incomplete. The solutions proposed are as fascinating as the problem itself. Perhaps our understanding of nuclear reaction rates in the first few minutes needs a subtle tweak. Maybe an unknown form of particle physics, such as certain interactions of dark matter, could have destroyed some of the lithium after it was created. Or it's possible that these ancient stellar atmospheres are not perfect time capsules, internal processes within the stars themselves over billions of years might have slowly mixed the surface lithium down into hotter interior layers where it was destroyed. Resolving this tiny discrepancy is a major goal, as it could be the thread that unravels a much larger tapestry of new physics. Beyond these primordial elements, isotopic ratios act as a detailed chronicle of later cosmic history. The elements heavier than lithium, all the way up to iron, were forged in the hearts of massive stars. Those heavier still, like gold, platinum, and uranium, require even more extreme conditions, such as the violent collisions of neutron stars or rare types of supernova. Each of these astrophysical factories leaves behind a distinct isotopic signature. For instance, the ratio of iron-60, a radioactive isotope with a half-life of 2.6 million years, to stable iron-56 found in deep-sea sediments on Earth, provides direct evidence that a nearby supernova exploded close to our infant solar system, potentially even triggering its collapse. Similarly, the abundance of certain isotopes of elements like europium or tellurium in ancient stars tells us about the specific type of star that first seeded the galaxy with those atoms. By reading this intricate isotopic code, we can piece together the history of our galactic neighborhood, understanding not just the initial conditions of the cosmos, but the dramatic stellar lives and deaths that enriched it over billions of years, ultimately providing the raw material for planets and life. This meticulous study of atomic nuclei, these tiny variations in mass, provides a direct and unbroken link from the universe's first fiery minutes to the present day, written in a language we are only just learning to fluently read. Deep within the hearts of the oldest stars in our galaxy, and locked inside the ancient meteorites that occasionally fall to Earth, ticks a set of the most reliable clocks in the universe. These are not clocks made of gears and springs, but of atomic nuclei, and they keep time through a process so steady it is virtually unchangeable: radioactive decay. This powerful dating technique, known as Nucleosynthesis, allows us to use the immutable half-lives of elements like uranium-238 and thorium-232 to peer back into the deepest reaches of cosmic time and independently verify the age of the universe itself. These heavy elements were not born in the Big Bang. They were forged in the most violent events imaginable, the cataclysmic supernova explosions of massive stars and the incredibly energetic mergers of neutron stars. When these events occur, they blast their newly created elements out into the surrounding galaxy, where they become incorporated into the next generation of stars. To use these cosmic clocks, astronomers perform a kind of stellar forensics on the most ancient stars we can find, often residing in the halo of our Milky Way. These stars are like cosmic time capsules. They formed from gas that was only lightly enriched by a few prior generations of supernova. By pointing powerful spectrographs at these stars, we can precisely measure the minuscule amounts of these radioactive elements in their atmospheres. The key measurement is the ratio between a radioactive parent isotope, like uranium-238, and a stable daughter isotope that is produced through its decay chain, like lead. Since we know the exact rate at which uranium decays into lead, its half-life is about 4.5 billion years, remarkably close to the age of Earth, we can work backwards. If we find a star that has a certain amount of uranium and a certain amount of its decay products, we can calculate how long ago that star formed with those elements already inside it. This provides a solid lower limit for the age of the galaxy, and by extension, the universe, because the galaxy cannot be older than the cosmos that contains it. The results of this meticulous work are nothing short of spectacular. Measurements of the uranium-thorium ratios in some of the galaxy's oldest stars consistently yield ages of around 13 billion years, with uncertainties that beautifully overlap with the 13.8 billion year age determined from the cosmic microwave background. This independent confirmation is a cornerstone of modern cosmology. It means that two completely different methods, one based on the expansion of the entire universe and another based on the nuclear physics within individual stars, arrive at the same profound conclusion about the age of everything. But Cosmochronology does more than just confirm a number. It opens a detailed window into the chemical evolution of our galaxy. The specific abundances of these radioactive elements tell a story about the rate at which the first massive stars lived and died, seeding the pristine cosmos with the first heavy elements. They can even hint at the frequency of those rare and dramatic neutron star mergers, which are now understood to be the primary cosmic forges for the heaviest elements like gold and platinum. The steady, irreversible tick of these atomic clocks provides a direct and tangible connection to the most violent and creative events in cosmic history, synchronizing the story written in the light of the CMB with the story written in the elements of the stars. But what if the universe in its entirety is not the vast, endless expanse it appears to be? What if its true nature is something far more intricate and strangely familiar? We naturally picture the cosmos as an infinite, simply connected void, a space where any path you could imagine eventually leads away from its starting point, never to return. Yet the fundamental geometry of the universe, its flatness, does not dictate its topology. It is a profound and often overlooked distinction. Geometry tells us about local curvature, like whether the angles of a triangle add up to 180 degrees, while topology describes the global shape and connectivity of space itself. A simple piece of paper is flat and has a simple topology, but if you take that same flat sheet and roll it up, connecting two edges, you create a cylinder still perfectly flat locally, but now with a multiply connected topology. Take it a step further, connect the other two ends of that cylinder, and you formed a torus, a donut shape. This object remains geometrically flat. If you were a tiny ant living on its surface, all your local measurements would tell you you're on a flat plane. But if you set off in a straight line, you would eventually return to your starting point from the opposite direction. This is the captivating idea behind cosmic topology, the possibility that our entire universe, while measured to be geometrically flat, might be finite and multiply connected, woven into a shape like a three-dimensional torus, or perhaps something even more complex, like a twisted cubic space or a dodecahedral universe. If our cosmos does have such a non-trivial shape, it would leave a ghostly but potentially detectable signature in the oldest light we can see, the cosmic microwave background. The logic is beautifully straightforward. In an infinite, simply connected universe, the CMB photons we receive have traveled on straight lines from the surface of last scattering, and each point on that surface is unique. But in a finite, multiply connected universe, space wraps around on itself. This means the sphere of the CMB that we observe could actually be intersecting with itself. A single, massive, ancient structure, like an enormous cluster of galaxies from the early universe, could actually be visible to us in two different directions on the sky. Its light would have taken two different, looping paths through the curved architecture of the cosmos to reach us. The most famous predicted signature of this is the appearance of matching circles in the CMB. Astronomers would search for pairs of circles on opposite sides of the sky where the pattern of temperature fluctuations is nearly identical, a telltale sign that we are looking at the same region of the primordial universe from two different perspectives. Other, more subtle signatures could include specific patterns of correlated fluctuations on very large angular scales that wouldn't occur in a simply connected, infinite space. The hunt for these topological fingerprints has been a serious and ongoing scientific pursuit for decades. Teams have meticulously analyzed the full sky data from satellites like WMAP and Planck, using powerful algorithms to search for these matching circles or correlated patterns. So far, the searches have come up empty. The universe, to the limits of our current observations and on scales larger than the observable horizon, appears to be simply connected. This null result is in itself a profoundly important finding. It places stringent lower limits on the size of the universe, telling us that if it is finite and multiply connected, the fundamental domain, the cell that tiles all of space, must be at least several hundred times larger than our observable horizon. We are effectively trapped in a cosmic cell whose walls are so distant that their light hasn't had time to reach us, and may never will due to the accelerating expansion. Yet the search is far from over. The absence of evidence is not evidence of absence, and the possibility remains one of the most tantalizing in all of cosmology. A confirmed detection would be nothing less than earth-shattering. It would provide our first ever glimpse of the global structure of the entire cosmos, a scale beyond the observable universe. It would be a direct message not from the inflationary era, but from the pre-inflationary universe. The specific topological shape would be a fossil from the universe's very first moments, perhaps even determined by the quantum fluctuations of gravity at the Planck scale, before inflation blew everything up. It would tell us that the entire universe is not just larger than what we can see, but that it has a specific, finite, and potentially knowable architecture. The philosophical implications are staggering. A finite universe, one with a defined shape and size, feels fundamentally different from an infinite one. It invites questions about what lies beyond its mathematical boundaries and challenges our deepest intuitions about the nature of reality itself. It suggests a cosmos that is not a formless void, but a structured entity, a finite object with a specific form, echoing the planets, stars, and galaxies within it. Now, let's turn our attention to one of the most foundational assumptions in all of science, the idea that the laws of physics are immutable, that the fundamental constants which dictate the strength of forces and the masses of particles have been the same everywhere and for all time. This principle is the bedrock upon which we've built our entire understanding of the cosmos, from the quantum world to the largest scales. But what if this bedrock isn't as solid as we believe? Imagine the fine structure constant, a number that governs the strength of the electromagnetic force, subtly changing over billions of years. Or consider the proton-to-electron mass ratio, a value that sets the scale for all of chemistry, slowly drifting over cosmic time. The confirmation of such variations would be nothing short of a scientific earthquake, forcing a complete rewrite of physics and challenging our most cherished notions of a stable, uniform universe. The methods scientists use to test this radical idea are feats of modern precision engineering and observational astronomy. One primary technique involves using the universe itself as a giant laboratory by looking back in time. When we observe the light from incredibly distant quasars, it has traveled for billions of years to reach us. Along its journey, it passes through ancient clouds of interstellar gas. These clouds absorb specific wavelengths of the quasar's light, creating a unique barcode of dark lines in the spectrum known as absorption lines. The precise positions of these lines are exquisitely sensitive to the values of the fundamental constants at the time the light was absorbed. By comparing these ancient barcodes to the ones we create in our laboratories today, we can search for any tiny shifts that would indicate the constants were different in the past. Another powerful method takes place right here on Earth, using the most precise timekeeping devices ever built, atomic clocks. These clocks rely on the ultra-stable vibrations of atoms, frequencies that are directly tied to the values of constants like the fine structure constant. By comparing different types of atomic clocks over months and years, researchers can hunt for any evidence that these constants are slowly drifting even in the present day. The results from these painstaking experiments are tantalizing, controversial, and far from settled. One team, after analyzing quasar light from over 300 telescopes, reported evidence that the fine structure constant was very slightly smaller in the distant past, and that this change varied depending on which direction they looked in the sky. This would suggest not only that constants change, but that the universe might have a preferred direction, a concept that would RADIC at LLY Chinese letter our understanding of cosmic isotropy. However, other teams using different methods or reanalyzing the same data have found no such evidence, attributing the potential signal to systematic errors or undetected biases in the measurements. The debate is fierce and ongoing, a testament to the extraordinary difficulty of measuring such a subtle effect across billions of light years. This is the very frontier of experimental cosmology, where the signal being hunted is at the very limit of what our technology can discern. If these variations were to be confirmed, the implications would cascade through every field of physics. The most straightforward explanation would be that these constants are not truly constant at all, but are instead dynamic fields that evolve slowly over time, much like the Higgs field or the theorized quintessence field for dark energy. This would immediately connect the world of particle physics to the large-scale evolution of the cosmos in a completely new way. Even more profound is the link to string theory, which posits the existence of extra-spatial dimensions beyond the three we experience. In many string theory models, the fundamental constants we observe are not primary. They are the result of how these extra dimensions are curled up and shaped. If the constants are varying, it could mean that the geometry of these hidden dimensions is itself slowly evolving, providing our first ever experimental handle on a theory that has long been considered mathematically beautiful but untestable. This would bridge the gap between the quantum gravity of the very small and the cosmological history of the very large, offering a unified vision of physics that has eluded us for a century. This concept inevitably forces a profound philosophical shift. We are accustomed to a universe governed by fixed, eternal laws, a stable stage upon which the cosmic drama unfolds. The discovery of evolving constants would reveal a stage that is itself dynamic, its very properties changing over time. This would reshape our understanding of the universe's unity, suggesting that the laws of physics are not written in stone but are more like local ordinances that can change with time and potentially with location. It would challenge the Copernican principle that we do not live in a special place or time, as we would have to consider that the physical laws we measure today might be unique to this epoch in cosmic history. The stability we perceive would be an illusion on a cosmic timescale, forcing us to view the universe not as a static entity, but as an evolving system whose most fundamental rules are part of its ongoing story. This leads us directly to a final, overarching principle that seeks to explain why these rules, whether constant or variable, seem so perfectly tailored for our existence. This brings us to a final, deeply profound way the early universe might be speaking to us, not through a specific particle or force, but through the very conditions that allow us to be here to listen at all. It's the idea that the cosmos appears to be exquisitely, almost miraculously, fine-tuned for the existence of life. This observation is known as the Anthropic principle. In its simplest form, it states that the universe we observe must be compatible with the existence of conscious observers, because we are here to observe it. At first glance, this might sound like a tautology, a simple statement of the obvious. But when you dig into the physics, this principle transforms from a triviality into one of the most startling and debated concepts in all of science. Consider the fundamental constants that govern reality: the strength of gravity, the power of the electromagnetic force, the mass of an electron, the energy of the Higgs field. These are not predicted by any current theory. They are parameters that we must measure and plug into our equations. And yet, if any one of them were even slightly different, the universe as we know it would be impossible. If the gravitational constant were a tiny bit stronger, the universe would have collapsed back on itself in a big crunch long before stars could form. If it were weaker, matter would never have clumped together into galaxies. If the strong nuclear force were just a few % stronger, all the hydrogen in the early universe would have fused into helium and then into heavier elements, leaving no fuel for long-lived stars like our Sun. If it were weaker, protons and neutrons wouldn't bind together, and no atomic nuclei would ever form. The cosmological constant, the energy of empty space driving the universe's acceleration, is perhaps the most famous example. Its value is so incredibly small, yet not zero, that it seems to have been dialed in with unbelievable precision. If it were even slightly larger, the repulsive force would have blown the universe apart before any structure could form. These are not isolated coincidences. It's a long list of seemingly independent numbers that all have to fall within a razor-thin range of values to allow for a universe that is old, structured, and life-giving. This incredible fine-tuning presents a monumental challenge to physics. Why is the universe so hospitable? The Anthropic principle offers a framework for an answer, but it comes in different forms with vastly different implications. The weak Anthropic principle is a relatively uncontroversial selection effect. It simply notes that we can only observe a universe that has the properties that allow conscious life to arise. We shouldn't be surprised to find ourselves in a universe with a certain age, a certain type of star, and certain physical constants, because we couldn't possibly find ourselves in one that doesn't. It's a useful logical filter for interpreting our observations. The strong anthropic principle, however, ventures much further into speculative territory. It suggests that the universe must have those properties that allow life to develop at some point in its history. This version often carries teleological overtones, implying a purpose or design behind the cosmos, an idea that sits uncomfortably for many scientists as it lies outside the realm of testable science. Where the anthropic principle becomes a powerful and, for some, a necessary tool for modern cosmology is when it is combined with the theory of the multiverse. If our universe is just one bubble in a vast, perhaps infinite, multiverse, a cosmic landscape where each universe is born with a random set of physical constants and laws, then the fine-tuning problem simply evaporates. In such a scenario, the vast majority of universes would be stillborn or barren, collapsing instantly or expanding into empty nothingness. But in an infinitely varied multiverse, a tiny, tiny fraction of universes will, by pure random chance, have just the right combination of constants to allow for stars, planets, and life. We, of course, find ourselves in one of those rare habitable universes. There is no fine-tuning, there is only a selection effect on a cosmic scale. Our universe isn't designed for us. We are simply the inevitable product of a universe that, by chance, had the right ingredients. This idea gains traction because it is a natural consequence of theories like eternal inflation and string theory, which predict a vast plurality of universes. This perspective fundamentally informs and even redirects our search for a final theory of everything. Instead of asking, why do the constants have these specific values? A multiverse-based anthropic principle leads us to ask a different question. What is the mechanism that generates the diversity of universes, and what is the statistical distribution of their properties? The goal of fundamental physics shifts from predicting the unique values of our constants to explaining the landscape of possibilities. It suggests that the deepest laws of nature may not determine a single universe, but rather a framework that generates a vast ensemble of them. This doesn't make the search easier. It makes it different and, for many, deeply unsatisfying, as it seems to replace a fundamental explanation with a statistical one. Yet, it provides a compelling, naturalistic framework for understanding the most bizarre coincidence in all of science. The universe speaks to us through its suitability for life, not as evidence of design, but as a clue pointing toward a reality far vaster and more strange than we ever imagined. A reality where our entire cosmos is just one tiny leaf on an infinite tree of possibility. As we've journeyed through these 24 profound ways the early universe speaks to us, a breathtaking tapestry of connection begins to emerge. The cosmic microwave background radiation isn't just an ancient snapshot. It's the very canvas upon which the story of dark matter's gravitational scaffolding was painted. A story later confirmed by the precise clustering of galaxies we map in large-scale structure surveys. The primordial abundances of hydrogen and helium, forged in the universe's first 3 minutes, aren't isolated relics. They are the foundational ingredients that dictated the formation of the first monstrous population, 3 stars, whose explosive deaths then seeded the cosmos with the heavier elements we find in ancient meteorites today. Each whisper doesn't just tell its own story. It corroborates and enriches the narratives of the others, creating a web of evidence so strong and interlinked that it forms the bedrock of our entire cosmological model. This beautiful synthesis reveals a cosmos that is fundamentally legible, a universe that has encoded the story of its own origin and evolution into every layer of its existence, from the grandest galactic superclusters down to the isotopic ratios within a single atom. The quantum fluctuations that were stretched to cosmic proportions during inflation left their fingerprint in the CMB's temperature variations, which then became the seeds for the Baryon acoustic oscillations we see frozen in the distribution of galaxies, which in turn allows us to measure the accelerating expansion driven by dark energy. It's a single, continuous chain of cause and effect, a narrative that stretches from a trillionth of a second after the Big Bang to the present day, and it demonstrates with stunning clarity how the physics of the unimaginably small is inextricably woven into the fate of the unimaginably large. What makes this synthesis so powerful is that it isn't based on a single, fragile line of evidence. It's a convergence. The age of the universe derived from the expansion rate measured by the CMB agrees with the age determined by the oldest stars and the radioactive decay clocks within them. The amount of ordinary matter calculated from the primordial deuterium abundance matches the amount we infer from the Baryon acoustic oscillation scale. The existence of dark matter is demanded simultaneously by the rotation curves of galaxies, the gravitational lensing of galaxy clusters, and the specific pattern of fluctuations in the CMB. This isn't a house of cards, it's a cathedral of knowledge where each pillar supports and strengthens the others, creating a coherent and robust picture of a dynamic, evolving cosmos that has actively preserved a record of its own past. This interconnected narrative does more than just satisfy our scientific curiosity. It fundamentally reshapes our place in the universe. We are not passive observers looking out at a cold, silent void. We are active participants in a grand, ongoing story, literally made from the ashes of those first stars, our bodies carrying the isotopic signatures of ancient supernova. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was forged in the nuclear furnaces of stars that lived and died long before our sun was born. We are the universe become conscious, able to look back across 13.8 billion years and decipher the subtle messages it has left for us, encoded in light, in matter, and in the very fabric of space-time. This synthesis empowers us to see that the past is not a distant, abstract concept. It is actively present in the world around us and within us, a continuous thread connecting the fiery birth of the cosmos to our own moment of awareness here on a pale blue dot. As we reach the end of this cosmic journey, let's pause for a moment and reflect on what we've uncovered. We've ventured from the first flash of light captured in the cosmic microwave background to the ghostly whispers of relic neutrinos, from the gravitational waves rippling through space-time to the elemental fingerprints in our very bodies. Each of these 24 messengers is a thread in the same magnificent tapestry, telling a story that stretches back nearly 14 billion years. This isn't just abstract science, it's a profound reminder that the universe is actively communicating with us, and we are now learning how to listen. Every time an astronomer points a telescope at a distant quasar or a physicist analyzes data from a particle detector, we are tuning into a conversation that began at the dawn of time itself. The progress we've made in cosmology is nothing short of breathtaking. In just the last few decades, we've moved from simply confirming the Big Bang to mapping the subtle ripples it left behind, from theorizing about dark matter and dark energy to measuring their influence on the evolution of everything we see. We've built observatories that can detect the faintest gravitational waves and satellites that can measure the polarization of ancient light with unimaginable precision. This relentless curiosity, this drive to understand our place in the cosmos, is one of humanity's most beautiful qualities. It connects us to those first stargazers who looked up at the night sky and wondered, and it pushes us toward questions that probe the very boundaries of reality, seeking a theory of quantum gravity and perhaps even clues to a multiverse. So the next time you find yourself under a clear night sky, away from the city lights, take a moment to truly look up. Let your eyes adjust to the vastness, to the countless points of light, each one a sun, each one a possible world. And know that you are not separate from that grandeur. The atoms that make up your body were forged in the hearts of those stars. The hydrogen in the water you drink is a relic from the universe's first 3 minutes. You are literally made of stardust, and the same physical laws that govern the spin of distant galaxies also govern the electrical impulses in your brain that allow you to marvel at it all. You are the universe becoming conscious of itself. This journey doesn't have to end here. The conversation continues, and you are a part of it. We'd love to hear which of these cosmic echoes resonated most deeply with you. Was it the ancient light of the CMB, the mysterious pull of dark matter, or the mind-bending idea of quantum fluctuations shaping the entire cosmos? Let us know in the comments below what captured your imagination. If you enjoyed this deep dive into the mysteries of space and time, please consider subscribing to the channel and hitting the notification bell so you don't miss our next exploration. There are always more secrets to uncover, more wonders to explore. Thank you for joining us on this incredible adventure through space and time. Until our next journey, keep looking up, stay curious, and never stop wondering about the magnificent universe we call home.